Welcome to the lecture series on soft computing in computer science. This is the session where we are going to discuss more about the case studies of fuzzy logic systems applications and how to implement that application using MATLAB environment. This is part 3, and in part 3 we are going to deal and we are going to discuss two control systems. One is fuzzy PID control, another one is fuzzy based DC motor speed control. First one, fuzzy PID control. What is this PID control? Proportional integrative derivative controller. So this is very popular controller, and this PID controller are classical controller which is very simple in their operation and low cost. But when we integrate fuzzy logic into this PID control, why? Because to enhance its ability to translate the operator control action into a rule base. But in the previous case we have only the adjusted value, but the adjusted value we need to take why this value is adjusted, what caused the value adjustment so far. So that case we need to know about the idea of fuzzy logic. So here in this presentation an attempt is made to explain the working of classical PID controller. Then you are very well know about what is fuzzy logic. Then the idea of fuzzy logic controller and how this fuzzy logic controller advanced the operation of classical PID controller, and finally the mathematical working of fuzzy PID controller. All these things we are going to see in the understanding of fuzzy PID control. PID controller. What is this term PID stands for? So it is a 3-letter term and it stands for proportional integral derivative. The combined output of all 3 branches. So in a control system you have 3 control units, one is P, another one is I, another one is D. These 3 are combined and it is fed to the plant. What plant? That plant may be of any system of operation until the desired set point value or the error signal is constant at 0. So if you achieve the desired set point value or the error signal is 0, that means there is no error. So this in that aspects, these 3 values, proportional, integral and derivative values are, there is a black diagram of this PID controller. So this is the black diagram of the PID controller. So you are setting the value here, you are setting the value may be either minus or positive sign, and it has been summed for the system operation. Suppose if the system operation has error, the error has been divided into 3 kind of error. One is proportional error, integral error, derivative error. So 3 kinds of error, and these 3 kinds of errors are summed up and given to the process. So it produces the output is again fed back. So this is the way in which the system is operated. So Kp, Ki, Kd, these 3 are constant. Other things are from the system, E of t, integral E of t dt and d by dt of et. These 3 are the values that is generated by the system. But what we need to identify is Kp, Ki, Kd. These 3 values we need to understand in order to know the smooth operation of U of t. So this is the way in which you need to make a note of the PID control process of a fuzzy system. So the proportional branch takes the error signal as input and outputs a signal proportional to the same. Yes, of course, the black diagram, that is what we have seen. The integrated block outputs a summation of all previous errors multiplied by a suitable gain factor. See, the statement here is nothing but the explanation of the architecture of the PID controller in the previous slide. So the derivative measures the rate of change of error and hence outputs the same multiplied by the gain factor. So the time domain representation is as follows. What is that? PID challenges. So the mathematics in a PID control equation is complex with multiple variables and constants interacting. Yes, of course. These issues common to almost every process control applications. See, these things are very common to almost all complicated industrial applications. So, what are those? Time delays or lag, step function response, ramp and soak function response. So, these three things is very essential, because when you want to control any process, any control applications, you face these three things: delay in time, or otherwise called by the name lag. We used to call the name how much lag it is, right. So, and the response of the step function as well as the response of the ramp and soak function. These three things are needed. So, in many situations the output can take a long and perhaps also variable time to react to input changes. That is the generic scenario. If you are expecting an output, so the output is not produced immediately and we have to wait for a so long time, because the variable as well as the time needed to have some time to change the input. To give one example, let us understand this statement, why this situation is by means of one example. If you are having a furnace and if you want to cool that furnace when charged with the new metal, see, obviously it could take several minutes to come back up to the temperature. So, this can lead to temperature overshoots. Yes, you can face that, you can experience that, which may damage the contents. When the target value changes instantaneously, say for example, if you want to, if you are observing the system and in that observed system, if the target values are changed instantaneously, what this PID will do is the PID will forces the system. Yes, of course, it will try to force the system. Why? Because we need to apply a large correcting factor, because this so much of correcting factor is needed, because this will lead to overshoot. So, when you operate this PID and when you change the target value instantaneously, you may face these kind of consequences. So, how to incorporate the fuzzy logic with the PID principles? So, this is the overall principles of the PID controller. How? So, if you look at the classical proportional plus integral plus derivative, see, class proportional plus integral plus derivative PID, it is still the most widely adopted method in industry for various applications. Why? Because of its simple structure, ease of design and low cost implementation. Of course, still they are using the PID controller for controlling. However, this PID controller is linear, but most of the current systems are not linear and it is highly non-linear and it contains lot of uncertainties. So, this traditional PID controller fails for such kind of systems and it is not suited. So, what you can do is you can associate fuzzy idea into the PID. So, the fuzzy PID control is treated as an another way or alternative way to PID control, because this is in general tries to find the suitable values for Kp, Ki and Kd, because there are some techniques and algorithms that can be used to tune this PID in association with the fuzzy, and it can be demonstrated further that returning to a necessary value. So, here there is no need for a skilled human operator. In the previous case, when it is operated only with the PID, we need a skilled human operator, and that skilled human operator will do the adjustment process and all while performing the controller process, while applying the controller to a process. But in this case, this is not necessary. So, this the schematic diagram or the generic architecture diagram of a PID controller is, the fuzzy controllers have been applied to industrial process with some degrees of success, where the rule buffer codifies the experience of a skilled human operator. So, here we have an error, a proportional error, integral error, derivative errors, all these errors, and this is very dynamic in nature while the system is in operations, and these are given to this fuzzy block. The fuzzy block will tries to quantify that error as a negative low, negative large, negative low, negative medium, 0, like these kind of linguistics, and this is again inputted to the fuzzy system. Then finally it will taken to the C system, final value has been taken. So, likewise this can be adjusted the error is quantified using the fuzzy approaches, and the quantified values are fed into the inference system in order to get the defuzzified value to effectively control the system. So, the fuzzy PID control, you can say that it has a dynamic part, and based on the diagram, the dynamic part involves error calculation. It calculates the error EK, and it has a integrated, it computes the integral of the error, and it has a derivative, it computes the derivative of the error. So, this is very dynamic in nature. That means when the system is operating, the values are also getting keep on updated. And the static part you can do is what is that? You can convert the GRISP input. What is the GRISP input? Error integral. See, that is the GRISP value can be converted into fuzzy value, and for each linguistic value you can associate a membership function. And you have inference, and this inference always uses the fuzzy rules, so that the fuzzy inputs generate the fuzzy outputs. And the defuzzification is nothing but converts the fuzzy. If the output is fuzzy, then over the fuzzy you have to apply the defuzzification method in order to produce the GRISP control signal. Here you need to note down one thing, that is gain update. So, what is this gain update? So, the gain update is how much gain that we have achieved while adjusting the control signal. See, the system has some requirement, and based on the system requirement we need to adjust the control signal. While adjusting the control signal, we least in a position to receive the update about the gain. So, this is what you know. So, here there are some steps that has been mentioned when understanding the fuzzy. So, what are the two variables that has been taken? Error, that is treated as negative large, negative small, 0, positive small and positive large, and the change in error, it is also negative large, negative small and so on. So, these two things are, so error is taken and the change in error is calculated. So, how these membership functions are defined? Negative low using the trim of member function, and these values are associated with it. So, negative low, right, and negative large, negative low, negative small, 0, positive small and positive large. So, this is negative large, negative low, negative small, 0 and positive small and positive large. This negative small has, see, -1, -0.5 and 0, like that. So, like that you can define all these things values, right. So, this is the way in which the membership function has been quantified for the each and every variable. Fuzzy rules. If EE is NL and change in error, if error is negative low and change in error is also negative low, then what is this UU? That is the adjustment of the system, positive low. So, this is the rule that has been taken up for in generic PID control system, and this error is calculated while you are executing the system with membership function as well as the rule, and when the rule is fired according to the Mamdani inference system, you may observe that there is an error difference. What is the error difference? We may set the point, that is our desired set point, and we may find the difference between the current temperature. So, what you have to do is you have to change the error and the change in error into fuzzy values using the inference functions, and you need to apply the fuzzy rules and control. So, this is the generic step that you need to follow for understanding the thing that has been there in between that. So, what is the next step in understanding the idea? So, when you are applying this fuzzy PID control and when you want to design the system in MATLAB, there is an environment called Simulink. Using this Simulink environment, you can design any PID control system by placing the control over the system. Then accordingly you can design the KP value, KI value and KD value. So, if you are not able to set KP, KI, KD value, and if you want to tune that KP, KI, KD value and you want to observe the system at what optimal value of KP, KI, KD the system is executing properly. In that case, the problem of finding the suitable value for KP, KI, KD can be treated as an optimization problem, and the genetic algorithm can be used in that place, right. Sorry. The next important case study or the application of fuzzy logic system is how a DC motor speed can be controlled in a fuzzy logic based approaches. So, you know that a DC motor is used to derive a load and the speed of the motor needs to be controlled. That this is the most important thing. A DC motor is used to derive a load and the speed of the motor needs to be controlled. The desired speed is set by the user and the controller adjusts the voltage applied to the motor to maintain its speed. So, the desired speed is set by the user and voltage. The speed and voltage are the two input parameter, and what is that need? How the motor maintain its speed. So, that is what we need to discuss. So, if you understand the DC motor control with the physiologic control, see there is a reference speed. So, in the previous case sensor is there that senses the external node. So, here in a reference speed, and that reference speed is error is estimated over which fuzzy controller is applied. So, now the DC motor is connected with that. So, based on the input its value is adjusted and that value is we have got the output here. So, the DC motor speed control can be effectively controlled and adjusted and monitored with the help of the fuzzy logic system, and this is the diagram, and where this diagram can be drawn using the Simulink in the MATLAB environment, and of course it is published in the conference in the year 2016, right. So, this is basically the idea in which how a DC motor speed control can be obtained and how it is maintained over the operation for controlling the speed of the DC motor using the fuzzy logic based approaches. So, you have all the variable that is intact with the system, and all these intact with the system that can be designed in the Simulink environment by using the plug and play tools, and it is very easy to follow that also. So, when you talk about the diagram, it may easily understand that this system that we have seen is aimed to regulate the speed of the DC motor. In what way it is? It tries to adjust the input voltage based on the error between the reference speed and the actual speed. So, it tries to adjust the voltage based on the error as well as the reference error. So, these two things are needed in order to adjust the input voltage based on the error. So, this particular why this is effective, again I am saying that this system, when you talk about the operation of this system DC motors control, the values that are needed to control the speed of the DC motor system, if you plot the values in a system or in a graph, you can find that there are non-linearities. So, it cannot expand it on its own, it has and another thing is it have a lot of uncertainties. We may not say this is the actual style of the input values, and the input values are gradually increasing and it is follows a certain phase, certain fashion, and you can observe it very clearly. When this is the first value, definitely this will be the second value. When this is the second value, definitely it will be. So, like that it do not have any periodical pattern. So, in that case we may find lot of uncertainty. We are not sure about what is the next value, and what we cannot very confidently say that this is the next value. So, in that case you may find that the system may contain lot of non-linearities as well as a lot of uncertainties. So, obviously whenever you find a system that has non-linearity, uncertainty, so fuzzy automatically comes into the pictures. So, we can divide that diagram into several key components. From the diagram that what has been given for that Simulink diagram, you may say that there is a space called reference speed input. So, the reference speed input is the section where we can calculate the desired speed that we want to motor to achieve. So, this speed my reference my motor should run. So, that is the speed, that speed is called reference speed. Now, actually the motor is running, right, it has its own speed, that is the actual speed. That actual speed as well as the errors reference speed, we can find the difference, and that difference is nothing but error calculation, and this error should be within the limit, it should not go beyond that limit. So, always the fuzzy logic control will try to generate or will try to process the error and try to control the signal. So, that thing is very important, that is you need to very meticulously control the system. So, that is very essential in order to need the control the system, right. So, now what is the control gain? So, what is the control gain? The control gain is the one that amplifies the control signal before applying it to the motor. So, you have the control signal, and if you want to control the signal, and that if you do that before applying it to the motor, so what you can do? You have a DC motor dynamic model, and this DC motor dynamic model trying to simulate the behavior of the DC motors. That one thing you should understand from the picture. Another one is load torque. Load torque. What is this load torque? This load torque is the one that represents the external load acting on the motor. So what are the things that you need? So first thing is it's behavior of the motor, second thing is amplification of the control signal, and the third one is how the external load is acting on the motor. So based on that, then you have to display the motor speed and its associated performance metrics. So this is what that you need to understand that. So one is control gain, another one is motor model, another one is load torque. So the objective of the motor control system, what is this objective? See, our objective is to the motor speed has to be maintained based on that we set some set point value, right, desired set point. According to the desired set point value, the speed of the motor has to be maintained. Even when you face some disturbances or any changes in the load, the motor speed should be maintained based on the desired set point value. So the duty of the physiologic controller here is to adjust the voltage. It tries to adjust the voltage. That voltage level should sit between the error and the change in error. So error as well as the change in error. So accordingly the voltage should sit between that. So the duty of the physiologic is to do that. It has the error and it also has the change in error. So between the error and the change in error, the voltage has to be adjusted, and it is the duty performed by the physiologic controller. So how this physiologic controller has been designed? So I have an error and I have a change in error. So these two are input variables and I need the control output. So the error is like this, negative low, negative small, 0, positive small, positive large, right. So this error is quantified as 5 linguistic variables for which all the cases are treated as a triangular membership function, and another one is change in error, and final one is control output U. So this is see triangular, remember error is treated as a triangular MF, as well as the change in error is also treated in the form of triangular MF, like what we have discussed in the PID controller. There also some adjustment is required, that means error adjustment is required. Here also the error is here this error is desired error and the error that what we have obtained. So that is the change. So all these things we can do, we can adjust this manner. The control parameter is also having. So we have now two systems, one is error, another one is change in error, and this change in error, this two is change in error is trying to control the output U. So this is what the membership function has been designed. After designing the membership function, what we can do is we can design the rules. So again I am saying that the rules are predefined and the rules are given in prior. You can just code that rule, and there are other methods are also available how to produce that error, how to produce this rule from either from the data or from some other approaches that we can discuss later. So overall steps, we for every adjustment we need to calculate the error. The error is nothing but the desired speed as well as the current speed of the motor. Accordingly we have to calculate the error, and that error is converted into the falsified value, the error as well as change in error. For each and every value you have to apply the inference, that means fuzzy rule and membership function put together, the Amdani inference engine is explode, and we are this generating the fuzzy control, and the fuzzy control is a falsified value, and this falsified value is adjusted in order to produce the defalsified value, and this defalsified value can be again taken back for understanding the error between them. So to illustrate, to understand the performance of this fuzzy based motor control, we can have something like what is the initial speed, 0 rpm, what is the decision speed, 100 rpm. So we can then what is the time step, 0.1 second. So this Simulink model, what we have designed is we have to run it for 100 timestamps and observe how the physiologic control adjusts the motor speed and reaches the maintained desired speed. So you have to record all these values. So this is the one like what we have discussed in the fuzzy PID control the same way. Accordingly the error has been calculated. See, initial speed 0 ppm and desired speed time simulation duration 100 step. See, for 0 timestamp the 0 is the error is 100, so no signal is. So likewise for when we increase the time step and the speed is also getting increased and the error is getting decreased, speed is also getting increased. So we observe that, see, the control signal is also producing some errors. Like this you can note down the values while executing the system. So what is that? see the time step is the current time step in the simulation, the motor speed and the error is also like that. So, the motor speed starts at 0 pm and the fuzzy logic controller works to bring up the speed to the desired. See, this is the idea. It starts at 0 pm, the fuzzy logic controller will tries to enhance that at the control pm. So, in between that operation, the control signal is adjusted based on the error and the change in error at each time step. So, that is the main thing, error and the change in error. So, over the period of time, if you could see that the speed of the motor will begin to move towards the what is the point that we have set, that means what is our desired value. And it is observed that while we are simulating the environment, it may cause the effectiveness of the fuzzy rule based system. You can easily understood about the effectiveness of the system. So, these three things is needed, time step, speed, error, finally the output, the control signal. So, with this we have come to end of the application of this part 3, application of fuzzy logic systems. So, this session we have discussed about two industrial control process, one is PID control in general, another one is motor speed control. This is the pure and pure control problem where the control signal controlled by means of error and a change in error. So, the system looks alike when the change error and change in error has been changed and the corresponding things is observed, and it has been observed and the values are recorded table, so that we can view and we can demonstrate or we can clearly understood that how this fuzzy logic control can be effectively utilized to overcome the traditional way of controlling the environment, either through PID or by the manual way of controlling the DC motor speed. So, with this the case studies related to applications of fuzzy logic system has been completed, and the topic what we have covered in the case study illustration, again the same thing will be covered through MATLAB environment, how the liquid level control, aircraft control, washing machine control, tipping problems, all these things will be illustrated through MATLAB executions environment, and this lecture will be continuing to in order to make know about the practical way of understanding the controlling process by means of fuzzy logic. Thank you.